As the demand for faster, smaller, and more efficient devices grows, the semiconductor industry faces a critical challenge: silicon alone can no longer keep up. Enter new materials like gallium nitride, GaN, and silicon carbide, SiC. These wide-bandgap materials are transforming power electronics. GaN, with its high-frequency capabilities, is making power converters smaller and more efficient. At the same time, SiC is ideal for high-voltage applications like electric vehicle inverters, operating at higher temperatures and voltages than silicon. Two-dimensional materials, such as graphene and transition metal dichalcogenides, are breaking new ground with their unique electronic properties. These ultra-thin, flexible semiconductors promise to revolutionize sensors, transistors, and wearable electronics. Their high carrier mobility and mechanical flexibility are key for future technologies. Meanwhile, cubic boron arsenide, CBAs, is emerging as a game-changer. With its exceptional thermal conductivity and good electrical properties, CBAs can effectively dissipate heat in densely packed circuits, paving the way for high-power electronics. Compound semiconductors like indium gallium arsenide, InGaAs, are finding applications in high-frequency communication devices and optoelectronics, essential for the 6G era and beyond. Their direct bandgap and high electron mobility make them ideal for lasers, photodetectors, and high-speed transistors. AI-driven material discovery is accelerating the integration of these advanced materials. By simulating countless combinations, AI helps identify optimal candidates for specific applications, shortening the path from research to real-world deployment. However, integrating these materials into the existing silicon-based infrastructure presents challenges. Lattice mismatches, thermal expansion differences, and interface quality are significant hurdles. Yet, innovative techniques like wafer bonding and epitaxial growth are being developed to bridge these gaps. The successful integration of these new materials is crucial for the semiconductor industry's future. They will enhance performance and enable entirely new applications, driving the industry toward unprecedented capabilities. As we venture into AI, quantum computing, and advanced telecommunications, these materials will be the foundation of tomorrow's technologies, redefining the limits of what's possible. The journey from silicon to a diverse set of advanced materials marks a new chapter in semiconductor manufacturing that promises to reshape the technological landscape for future generations.